I know that most of you got confused about the data sheet here. Okay, but before we start the data sheet, any questions about the lab itself, the animation, online animation? Okay, so but we do need to take a look at the data I have here. So I'll show you the screen that I have on one of my screen.
Real quick, Dr. Yang, are you teaching a Chem 2 class next semester or no?
Well, unfortunately, originally I was assigned as, but later on, I was told that, I need to teach Chem 1 again. So I'm not teaching Chem 2. Well, I really wish I could teach Chem 2 so we can see each other again. So, but that's okay. Okay, we will enjoy more in other faculty members Chem 2 class. But yeah. Well, if you want to take Chem 1 again, we'll see each other, right? Okay, all right. No, just kidding. Okay, so can you see this screen animation? Okay, so this is the data I collected, 26.81 degrees Celsius when I mix the 50 ml of hydrochloric acid and 50 ml of sodium hydroxide together. So essentially, I just did the experiment 1, and this is a temperature change. Okay, so I'll write that down so I can. But any questions about this part? So the temperature change would be 26.81 minus 20 degrees Celsius. It started as 20, so 6.81 degrees Celsius. That's our delta T. We need this data to do calculation. Now let me go back to my. Okay. All right. Essentially, I know that's this first row, the first part here might be a little bit confusing, but if you have a good understanding about the strong electrolytes, the dissociation of the definition of acid and base, then you should be able to understand when I explain it to you. HCl, it's an acid. In other words, it will give you proton and chloride. Okay. And sodium hydroxide gives you sodium and hydroxide. This is a definition of acid and base, species that can give you proton, species that can give you hydroxide anion. Now, initial mole of H+, remember, this is a strong acid, okay? When you take Chem 2, you will see the difference between a strong acid and a weak acid. Strong acid means the complete dissociation. In other words, this one will dissociate completely to give you H+ and chloride. There's no HCl molecule left in the mixture. Same thing for sodium hydroxide, 100% dissociation. What does that mean to us? If this is 100% dissociation here, originally it's 1 mole per liter hydrochloric acid. If this is 100% dissociation, then the concentration of H+ would be the same as original concentration of HCl. All right. It's sort of, if you want to treat this one as a stoichiometry calculation, you can do it. So essentially that's going to be 50 ml, convert that to liter. And this is a hydrochloric acid. And then molar concentration, 1 mole, 1 liter. And then molar ratio between the two is 1 to 1. Okay, so you have 1 mole of HCl, 1 mole of H+, and then you got the mole number of H+, and divide the total volume. It is still 50 ml at the bottom. Okay, then you will get the same amount of the concentration of the H+ as 1 again. Does that make any sense? You look very confused. Okay, all right. So I'm not wasting your time to do the the calculation of the H plus concentration. This is the mole number of the H plus. Volume, you know that, I mean, I guarantee, okay, 100% sure that it will give you 1 mole. All right, it's 1 mole. Oh, one mole. Yeah, so if you want to do the calculation here, well, actually, it would be nicer to 0.050 mole. Not concentration would be the same. Oops, concentration would be about the same, but the mole number is 0.050 mole. Okay. If you do the calculation of this divided by 50 ml converted to liter, it is still 1 mole of H plus. But anyway, so this is what and you can do the same thing for hydroxide. It will be, again, 0.050 mole. Okay, it will be from this part here. Very similar calculation. Now, limiting reactants. We know that if you mix those two together, HCl plus sodium hydroxide, this is the neutralization reaction plus water. If you write the net ionic equation, you will see all 3 reactions will give you exactly the same net ionic equation. And that will tell you something about the last column. Okay, you realize you can use the what I just said a moment ago to rationalize why you have a observation for this last column. Remember what I just said. All 3 of them have the same net ionic equation. Okay, so that will tell you something here. Limiting reactants. Okay, so we say that this one is 0.050 mole, 0.050 mole, right? So you treat each one of them separately to calculate how much of water will be generated. If you treat this one separately and assume that you have unlimited supply of OH minus, then it will generate 0.050 mole of water. And this will also generate 0.050 mole of water. So looks like they are the same. They are going to generate same amount of water. So now you can see that none of them are limiting reactants, or both of them are limiting reactants. Okay, so both of them will be consumed completely. There's nothing left for those 2 reactants. Does that make any sense? So this is a different, although we use the term here, limiting reactant, but this time it's different from what we did before. One would be excess, the other one would be the limiting reactant. So here you can see both of them will be consumed completely. So you can see either H plus, you can see H plus or OH minus. Okay. The reason why we have this column here is we actually, during the regular semester, we have 2 more experiments for you to run. And the last column would be the limiting reactant. Not the last experiment 5, there will be an excess reactant for one of them. So, but this is not the case for this experiment. Anyway, the yield of H2O formed in this case would be 0.050 mole, right? Now temperature initially would be 20.00 degrees Celsius, and then the 26.81 degrees Celsius, then 6.81 degrees Celsius. Okay, and then the mass of the solution. How do we do that? Okay, this is the well, you have 2 solutions together. Okay, but both of them are giving us volume. So when you deal with this kind of question, so you can treat the 1 ml equals to the density of the solution is, okay, I should not write this. The density of this solution is 1 gram per ml. In other words, 50 ml of solution is 50 gram, 50 ml of solution, 50 grams. So total would be 100 gram in this case. Okay. We are making some assumptions, which is not unreasonable here. Okay. It's even if pure water density at 4 degrees Celsius, it should be 1 gram per ml. We are not talking about 4 degrees Celsius, and we are talking about the solution, but it's okay if we assume that we have this, okay? The Q absorbed by solution, then in this case, remember Q M times CS, delta T, you know the mass of the solution, you know the CS, I think it's 4.18. I think it's joule per degree Celsius per gram, something like that, okay? But double check, I could not remember how much it's 184 actually, okay? 4.184, it's not that far off. All right, so then delta T is known, so this part will be calculated. Okay, now Q absorbed by solution. Q is absorbed by solution. Where does this Q come from, if I may ask?
It's going into the system. So,
Well,
no.
what do you mean get into the system?
Like it's being absorbed.
Okay, so let me put this way. I'll quickly draw a coffee cup here, and you have your solution right here. Let's just assume that this reaction happens inside this tiny box, right? Okay, so the solution thermometer right here, you can see the temperature of the solution increase, right? So when you talk about the calculation of the Q for solution, since delta T is positive, so the Q solution, that gives you Q solution as positive. It means it absorbs the energy. That tells you that, since the solution here outside this box is absorbing energy, then something has to donate or something has to release energy. So where does that energy come from? It comes from the reaction. So how much energy released by the reaction will be absorbed by the solution? Therefore, for the Q reaction here, it would be negative, and the value between the two would be the same. In other words, you calculate this part, you just need to flip the sign to get this one. Then that's it. And then delta H reaction here, you have the joule. Delta H reaction, remember we talked about this in the chart. Delta H reaction is Q, okay? But we are talking about the delta H reaction kilojoule per mole. So you use this number divided by the mole number of water. We did this kind of calculation in our lecture, if you happen to remember. It's just a little bit different setup.
Well, how do we know if we use the energy absorbed or the energy released?
Energy released, but can you see the reaction? This is reaction. Delta H reaction.
Okay. I never saw that part. Okay, never mind.
See those nodes, okay, bottom nodes, those tiny things will tell you something important. Okay, so that's how we solve this part. So anybody did the calculation of this Q here already? How much is that?
My data's different because I did the in-person, but I got 2.56 times 10 to the 3.
So did you use?
That was with my data.
Okay, yeah, I understand. Did you use this equation?
Yeah, I did.
Okay, so I'll just do a quick calculation and find out how much that is. All right, so that is 2849.3 should be, yeah, you can keep more digits. These are intermediate answers. Is this close to what you have, Ashley? Is this number close to what you have?
Yeah, I have about 2,500. So.
Oh, that's good. Okay, so
Yeah.
that's nice. Good enough. Good enough. All right, so this one would be negative 2849.304 joule, and this part would be, I'll write it here. Okay. So it would be negative 2849.304 joule divided by the mole number of water. Remember, this much of the energy is associated with this much of water generated. This last column is asking you the kilojoule, the energy released by the reaction for 1 mole of water generated. So that's why we have to do the last step here. So if you do that, okay, well, this is a 56986.08 joule per mole. Of course, if you convert that to kilojoule, then that's going to be 56 point significant figures. Well, looks like we have to use scientific notation. 5
Negative?
Negative, you are right. Negative 5 point, we should have 2 significant figures right here. So 5.7 times 10 to the 1 kilojoule per mole. And that's how we do it. And you will do the same thing for the following 2 columns, for the following 2 rows. What I can see here is each one of them, we all know them, okay? If we talk about them separately, this whole thing is just for a new, it's just all of them, all of the things we learned, what we are doing here is applying them to the specific reaction, okay? So that's the challenge, because most of the time students said that, oh, I can understand this when you explain it, but when you use them to solve problems, I could not, just get lost. Okay, well, 2 possible reasons. The first one is you do need more practice. The second reason is you do not have a good understanding of the mechanism behind what we did in our lecture. Okay. So that's the reason. And how do you solve those 2 questions? The first one is just do more practice. And when you do practice, it's not just like you finish your practice problems and threw that away. You have to think about what kind of things we used behind the equations, behind the concepts that we use to solve these problems. Okay, so let's just use the partial pressure, the question that we talked in on the last slide. It's not just like, oh, hey, we solve this question and we just get rid of that. If I were the person who encountered this partial pressure for the first time, I'll go to the concept map, the chart, and try to manipulate that to let it match with my understanding about this part. Okay. Only when you convert something to yourself, that's the time that you're learning. The passive learning is just repeat what I showed you. And for the concept map, oh, I would just use that. But active learning is to understand what I gave you, and then reorganize that to let it become part of yours. And that's the active learning. Okay. Any other questions?
I have a question about the post lab.
Right.
So we only have like 4 experiments.
Oh yeah, well, you have 4 experiments. You have 4 experiments.
Well, yeah, but like the lab or the post lab, it asked us to compare like experiment 1, experiment 4, and experiment 5.
Don't worry about the experiment 5. If it asks you about experiment 5, you ignore it.
Okay.
Yeah. Yeah, I'll fix the problem. All right, folks. Okay. Anytime you have questions, shoot me an email and I'll be there. Okay. And we can also meet online if you have any questions. Okay. All right, folks, I'll let you go. Don't let me hold you for too long. I know holiday is waiting for you. Enjoy your holiday. Eat a lot. Okay. And
Thank
yeah.
you.
All right. See you, folks.
Hi, Dr. Yang.
Bye, Ashley. Bye, Kelly.